This nice and short. This is the very first event of our thematic program in commutative algebra for the year. To introduce myself, I'm Adam Van Tool. I'm one of the main organizers. It gives me great privilege to introduce Mike Stillman, who is the Dean's Distinguished Visitor at Toronto, and he will be giving us a course on commutative algebra. So we're looking forward to it. Well, computational commutative algebra.
Yeah. Thanks a lot. And let's see. I guess, how do I want to get started here? Always the first time, it takes a little bit. So basically, this is going to be a course in computational commutative algebra and computational algebraic geometry. And probably more commutative algebra, since that's the content of the program. But since a lot of the stuff in commutative algebra is really designed for use in algebraic geometry, it makes sense to sort of do both of these things. For the people here or online, I have a survey that I'd like you to fill out. It's just a Google form that is put on, it's on the web page for the course. And it just is a very simple thing, so I can see who's here and what people's background is and things like that. So that would be great if you could do it. So I think already from here, I've got an idea of how many people know about Gröbner bases. Online, it's a little hard for me to tell where people stand. So I'm going to be paying more attention to the Google form, I think. And once I get used to doing both Zoom and in person, maybe that'll be better. But we'll see how. Hopefully, this will work out okay. Okay. So the basic idea of this course is to figure out in commutative algebra what can be computed and how to do it, and actually to do it, and so on. So we're interested in what can be computed. Well, not just what can be computed, but how to do it. Also, what can be computed in commutative algebra, and in some parts of algebraic geometry. I'm not going to assume a whole lot of algebraic geometry. So whenever we do things, actually, whenever we do something advanced in either one, I will probably do a workings person introduction to some of the topics, so that if you can go figure it out elsewhere and so on. For instance, how many people are comfortable or with extentor, for instance? Okay. So that's going to be a good one where we'll do a sort of a simple introduction that will be enough for this. Won't prove all the little things about it, but it will do that. And sheaf cohomology? Abelian categories. No. Okay, we're not doing any of these things for. Actually, we will be doing sheaf cohomology. It turns out to be very simple stuff from an algebraic, from a computational algebra point of view, but not right off the bat. Today, we're going to talk about Gröbner bases and their applications. We will not prove everything about this stuff, right? So there are some good texts for this. I think Coxwell and O'Shea is a pretty good one. Eisenbred's book on commutative algebra, chapter 15, is also a good introduction to this stuff. And another one, I kind of like this one. It's simpler though. It's Adams and Lustonow. I think I've got that right. And then maybe there's a couple papers that will be worthwhile later on as well. There are other books. This is just a smattering of it. If you want to get the definitions, that if what I do isn't completely clear, that would be good. One thing I do want to do in this course These are nice boards. Okay, so one thing I want to do in this course isn't just explain what is known or not and how to do it. I want to know how to take things that we don't know how to do and figure out how to do it. That could mean, so we want new algorithms. Now we won't be there right away, but eventually you're gonna see things. You're gonna ask yourself. This is one of your job, is to ask yourself whenever you see something in computative algebra is how do I compute that? And or do I care if I compute that? That's another question. But this kind of thing. So we want to be able to do that. I'm hoping that some of you are working on problems where you might have something that you're interested in computing, and so we could learn about that also. So that would be pretty good. We will use software. I'm kind of biased in this setting because I wrote one of them. So Macaulay 2 is what I will use. You are completely welcome to use anything else. But I do recommend, in general, learning more than one system and so on. So even if you use something else, it's probably good to learn how to do this one. And if you're using something else, I'd like to know about it and like to see what can do and so on. So Macaulay 2, but you can use anything, whatever you want. Okay, now question from for the Zoom audience. Can you read what I'm writing down on the board?
Yep.
Okay, good. So let's see, what other things do I want to say? Yeah, so anyway, this is the plan. So we're going to basically try to figure out what it can be computed. Now, it turns out that there's one algorithm, Gröbner basis, one concept, that allows us to do a huge amount of the stuff. It isn't always the best way to do something. In fact, oftentimes it's not, but at least you can do a lot of things with it. There's some stuff you can't do, and we'll figure out what that is. And also, every now and then we'll try to talk about faster ways of doing some of the computations as well. But it's still a good first place to start. So our first ring. So commutative algebra is a study of commutative algebras, rings, basically. Our first ring that we will be interested in for quite a lot of time is R is going to be K adjoin x1 to xn, or whatever variable names we want to call them. Okay, and here K is equal to a field. Oftentimes it will be the rationals or or a finite field, but it could be an algebraically closed field. It could be the reals or the complexes, except we don't know how to compute with the reals and complexes for real. So we can approximate things, but otherwise none of this stuff will work for approximate stuff so well. You have to do other things. Okay. Not only is this a good first ring, it's also the most basic ring that links algebraic geometry and commutative algebra. And so this is what we're going to be interested in. We'll be interested in ideals. The way we give an ideal is almost always to give a bunch of generators for it sitting inside of R. Sometimes it will be a homogeneous ideal, which means that all these things are homogeneous. And sometimes it won't be. For right now, we don't care if it is or not. Okay, so we have that going for us. But this is not the only ring that we're going to be interested in. And when we're doing algorithms for this, I want you to think about how would you extend these algorithms, or how would you actually do these things that we're trying to compute for this ring in other situations. So for instance, other rings that we will eventually talk about are things like the polynomial rings over the integers. Over the integers instead of over a field. Subtle things change and so on. A lot of things can be done. It's generally quite a bit more complicated oftentimes, but anyway, we have that. One also wants factor rings, so R modulo ideal. That we will be doing a lot of, actually. What other kinds of things? So these are quotient rings or factor rings. We also want to talk about localizations and work with those also. But there's also some non-commutative rings that are really useful when studying commutative algebra. So for instance, there's the exterior algebra. This is where you have xi times xj is equal to minus xj times xi, essentially. Okay, and things like that. So instead of being commutative, it's mildly non-commutative in the sense of, or graded commutative, if you will. So there's this, and it will turn out that some really cool ways of computing a number of things go through this. Likewise, there's Weyl algebras. So this is a ring like with you have x and you have dx, maybe y and dy, etc., where x I can never remember it and I didn't write it down. X dx and dx times x. The difference of these two things is either one or minus one. I always have to think it through because I just don't do it enough. Okay, but it's you figure out how this acts on a function, and it will turn out to be the identity or negative of the identity. Does anyone know offhand which it is? Yeah, okay. So anyway, so we can worry about that later. This Weyl algebra is really good for sort of algebraic analysis kind of things, but it's also good in commutative algebra. One thing that we will talk about is computing local cohomology later on. And it turns out to take these things that are horrendously infinitely generated and make them into finite computations. Not necessarily easy finite computations, but nonetheless, that's a pretty good way to do it. I think these are sort of good things to keep in mind. So we might actually be interested in much more general non-commutative things. A lot of Gröbner basis stuff works there. Typically, you lose finiteness in those situations. But anyway, this is kind of some of the stuff that we're interested in. So today we're going to go back and we're going to do R is k of x1 to xn. And the field is really not important at the moment, as long as we can compute in it. Okay, so and we are interested in basic questions about ideals. Oops, ideals, I forgot to write down modules over there as well. So we're going to be interested in computations involving ideals and modules and in the ring. So what are some of the things that we would like to do? Some very basic things. So suppose we're given I is equal to f1 to fn. I oftentimes like to use angle brackets for the ideal generated by a set of elements, but I oftentimes use parentheses by accident. So given that we have a number of questions that if you're just first learning this stuff, you should be asking yourself anyway, which I probably never did when I first learned it. Okay, so one of them, some questions. Is this the trivial ideal? Is I equal to, typically you write it as 1 instead of I equals R. I don't know why, but it's, in other words, i.e. is 1 in the ideal I. Can you take a combination of these guys, a linear combination where the coefficients are in R and get the unit out, the element 1? Given, let's say G in R is G in I. Okay, these are the basic questions about what Gröbner bases were originally designed to answer. And so this is that. What are some other questions? Well, for instance, if I and J are ideals, and we've got generators for both of them, what about I intersect J? Can we find generators for that? It's a reasonable question. Let's see, how much more of this kind of stuff do I want to do? Yeah, a little bit more, I think. So other things are, so consider the quotient R mod I. Okay. This is what most rings we consider will be like for the time being. So consider this. We want to do arithmetic in this. Here. I don't write elements as F plus I just write it as F, meaning that it's the image of that in there. But the question is, so is F congruent to G mod I, basically? Question mark. Well, that's exactly the same question as that. So so we want this. We would like maybe doing arithmetic in that is just this is the first thing that Gröbner bases give us. There's other things though, which I think we're going to. You might have the following situation. Here is, suppose we have a matrix R to the N to R to the M A, where A has entries in R. Okay, so it's a M by N matrix. I'm very specific about which order I do these things. The image vectors are always the columns of A, not the rows, okay? So unless we switch things around and do duals or non-commutative, we have to worry about that kind of stuff. But here, it's going to always be that. Find the kernel of A, aka the module of syzygies. Syzygy is the best word in the English language, as far as I can tell. But for word games, it has 3 Y's in it, if you don't make it plural, and that's it for vowel. That has the just great word. In fact, usually if mathematicians are playing word games, it's banned from use, is what I always find. So anyway, so can you calculate the kernel of this? So really not, it's not like linear algebra anymore. You know, you can't just do Gaussian row reduction. You sort of can, but that's what Gröbner bases are, and but not right off the bat. So then it becomes an interesting question as to how to compute this, and we'll talk about that maybe even later today. Okay, and it's going to go on and on. We want to know all sorts of things about this. This is just the very basic things. What else do we want to know? I don't know. There's a lot of things. I had. Let's just leave it at that for the moment. Any questions so far? Okay, this is just sort of getting into it here, and so on and so forth. What I want to do now is work up to question.
Hello. Yeah. So I just want to point out that regarding the Weyl algebra equation, probably for me an easy way that I could figure out the sign is to just apply the constant polynomial 1 to the left side, and you can figure out that on the right it should be -1.
That's a good way to do it, perhaps. Yes. That is a good way to do it. Thank you. So this should be -1. So I should have written it the other way at the beginning. Okay, good. Okay, so now, but there's tons and tons of other things we might want to do for ideals. When you learn commutative algebra, you start learning about the minimal primes of it, the associated primes of it, integral closures of rings, and all of this kind of stuff. These are all things with this and primary decompositions, we'll all do kind of stuff like that. Also, the homological algebra of these things, free resolutions, this thing here, syzygies, and so on. So all of these things are really important notions. There is one simple kind of ideal, though, where we don't need Gröbner bases for the most part. So so these are monomial ideals. So what we have here is, so again, R is our polynomial ring here, and a monomial ideal is going to be something like I is generated by a bunch of monomials. So for instance, here's one, a cubed, a squared b, abc, a squared bc, and this is contained in K adjoin ABC. Oftentimes the field, well, it actually does make a difference sometimes. But anyway, again, I'll use variables. I oftentimes use ABCs or XYZs or index things depending on the situation, but that's it. So it's just given by a whole bunch of monomials. So what are monomials looking like in general? So if alpha is n to the n, is in n to the n, then we have x to the alpha is x1 to the, I'm going to write alpha of 1 to xn alpha of n, because my alpha sub i's are themselves going to be vectors in a little while. Okay, so this is a power product. So a monomial is one of these, one of the x to the alphas. Okay. By the way, just in general, a term is going to be a constant times x to the alpha, where alpha is in n to the n, and c is in k. Okay. So sometimes you'll see different notation for these, but this will be what I use consistently. Monomial is just the x to the alpha, no constants. When we're over a field, we can pretty much deal with just monomials. If we work over the integers, this is going to become important. Okay, and other rings also. So, and then, okay, now you might have to move me over. Nope, you've already moved me over. Okay, great. So, I, given by x to the alpha 1 up to x to the alpha r, say, contained in R, is a monomial ideal. In other words, it's generated by monomials. And the question is we should be able to answer all these questions for that case. In fact, that's what Gröbner bases are going to be used for. A lot of times we're going to take a Gröbner basis, which will give us a monomial ideal. We'll do some operation there, and then hopefully it'll lift back to answers. It doesn't quite work that way all the time, but sometimes it does. Okay, so let's do some basics of this. Okay, one is 1 in the ideal I. How do I tell? I would have to have some multiple of each of these things be there. But if you think about it, these are all the only, by the way, what is 1? It's a monomial also. It's where the alpha is the 0 vector. Okay, so if that's in there, then it will be in the ideal. But it will, this is going to be the case if and only if 1 is equal to x to the alpha I for some I. Okay. That's the only way it can be, because if they're all higher degree, there's no way you can get down to degree 0. Okay. How about how do I test if I'm given if x to the beta is a monomial in R? Okay. So it's just a monomial. How do I tell if x to the beta is in I? Well, it certainly will be in there if I can multiply any of the monomials by that thing and get to my thing here. So this is if x to the alpha I divides x to the beta for some I. And that's if and only if. Okay, so that's the only way to get something that's in there. So after the first hour or so, I have a little worksheet that is online, and then you sort of think about some of these things more if you haven't ever thought about them. A third one that you might like are, what about minimal generators? A minimal generators is just a smallest number of generators that generate the same ideal. Okay, so which ones can I get rid of here? Like, can I get rid of any of these, for instance? Yeah, this one is equal to A times this guy. So this one I can ignore. I could get rid of that one. But none of these can I ignore. I need all of those. So basically, it's we take the minimal x to the alphas under division. Okay. So these are all pretty, I mean, they need much of any, they need a little bit of thought, but but not so much. One other interesting thing that is going to be important to us is something like the following. So if I is an ideal, and F is an element of R, then there's the ideal quotient, I colon F, which is called a colon ideal sometimes, or a quotient ideal. It's called all sorts of things. But what is it? This is equal to the set of all polynomials, G and R, or actually this is true for any ring, any commutative ring also, such that G times F is in I. Okay. It's actually pretty interesting. One way to compute this would be to enumerate all the elements of the ideal I, factor every single one of them, and then if it has a factor of F, then you can remove it and you can add the rest of it into the ideal. That is not particularly useful because there's an infinite number of these things, and factorization is a lot of work. So that's not really a finite algorithm, but nonetheless, we might be interested in this thing. And it turns out this is really a crucial computation that one needs to be able to do. Another one that's is important is I colon F infinity. This is the saturation. This is the set of all G and R, such that G times F to the capital N is in I for some N integer. Okay. In other words, I run through all the elements of I factor it out, and I get to not just remove one copy of F, but I have multiple ones. I can slice it out as well. Okay. So this is the colon ideal, and this is the saturation by F. I'll just write saturation. Okay, so we have those things. So the question is how do you compute that for monomial ideals? So for monomial ideals, so for a monomial ideal I, a monomial ideal, ideal I, which is given by x to the alpha 1 to x to the alpha r, and F is equal to a monomial, x to the beta, compute generators for I colon x to the beta, or I colon x to the beta infinity. How do you do that? So for instance, in our example, what is it? I is equal to a cubed, a squared b, abc, and I think that's it. And now let's take f to equal c. Okay? How do I calculate it from this? I can see some, by the way, every element in I will be in here. So this contains I at least. So it's going to contain all these guys. But if I find anything that's divisible by c, I get to take it as well. So I colon f, is this visible now on the screen, this corner? Yeah, it looks like it is. Okay, good. This is equal to, except I want to move it up a bit. I colon f is going to have a cubed in it. Going to have a squared b in it. But what about ABC? I get to I get to take the c and then take the what's left, AB. But this is not minimal any longer. This is a cubed and AB. Now, part of what you need to think about is this really, I mean, I can certainly take generators and do this. For a usual ideal, if you do that, it just doesn't work. I mean, there's hidden things in the ideal that are potentially divisible by F that you don't know. So are there any for monomial ideals? The answer is no. So it's easy to write down what this is. So we'll have you think about that later. I colon f infinity in this case is the same thing. So leave that. What about That was 4. Here's 5. What about the radical of an ideal? Remember what this is. This is the set of all g's in the ring R, such that g to some power is in the ideal I for sub n. Okay, so what is this for in this example? So in the example, the radical of I is equal to what? We have 3 generators. What's great about monomial ideals is usually things aren't hidden from you. So it's just right there. So what elements are in there? Well, a cubed, for instance, means that a is in there. Let's ignore that one for the moment. How about a squared b? What power of that will be, what power of a monomial will be in that, will be in this ideal, giving that a squared b? It's a times b, right? So a times b is, its square is a squared b squared, which is in there. And ABC is already, so it's basically taking the square-free part of each monomial. However, this is again, just like over here, this happens a lot when you do these operations, it's not minimal anymore. So what is this one equal to? Just to keep it real. Yes, by A. Okay. So that's that. Later on, we'll talk about it, but whenever you have a square-free monomial ideal, this is a pretty trivial one, but those are corresponding to simplicial complexes, and then we have some good technique for working with those as well. In fact, it's equivalent technique. And last one is, what about I intersect J? Suppose that I is equal to the generator of x alpha 1 to x alpha r, and J is equal to x to the beta 1, x to the beta s. So what is this equal to? It's going to be basically, let me say it this way, it's going to be given by the least common multiples of x to the alpha I and x to the beta j, like this. Wait, is that right? So least common multiple of 2 things is just take the highest thing. Actually, I should have written that down because that's exactly what we're doing in lots of these things. So I won't write it down, but we have the GCD of x to the alpha and x to the beta. I guess I will write it down. It's going to be the minimum. I'm going to write it as the minimum of alpha and beta, which means maybe I should write it down as the product of minimum alpha I and beta I, xi of that. And then the LCM of x to the alpha and x to the beta is just x to the maximum of alpha and beta. So x to the alpha times x to the beta is equal to the product of these 2 things, just like that usually happens for polynomials and things. Okay. So anyway, so we can compute this, and using this, you can write down generator solutions for all of this, which I'll ask you about later on. Okay. Now I think we're going to move back over here. Any questions about this stuff? And later on, you'll have to tell me how I want to get the level of it and so on as to what we're doing. But right now, yeah, so let's do 2 types of examples. The first one, if all the exponents of all the x to the alphas are 0 or 1, then I is called a square-free monomial ideal. Okay, these are one-to-one correspondence with all simplicial complexes, which you may have dealt with or not, but anyway. So here's an example. I is equal to, say, something like x1, x2, x2, x3, x3, x4, x3, x1, or well, okay. This is an example of an edge ideal, which Adam has done a lot of stuff with. So anyway, we have that kind of stuff going on. Another kind of ideal, which also I think Adam's done a lot with, is our ideals that are called strongly stable. So a monomial ideal, is called strongly stable. I always call it Borel fixed, but it's not quite correct. So I'm going to use this naming. If how do I want to say it? If whenever we have a monomial x to the alpha times x sub I is in the ideal I, okay? So whenever we have something like this, I'm just barring out one of the xi's. It doesn't have to be the last one or anything. It's just one of them. Then x alpha, I can replace it with xj, and that's in I. For all j less than, well, if it's equal to I, it's the same one. So for all j less than I. Okay. So for instance, so suppose so suppose I is strongly stable, and x1, which one did I choose? x2, x3 is in I. What other monomials are in there? Here. So think about it for a second while I erase this board. Then I contains what other things? So it contains x1, x2 squared. Yep. x1 squared, x2. Yep. x1 cubed. Yep. x1 squared, x3. Four, five. We're missing one. Oh, we're missing x1, x2, x3. Okay, so in fact, this would be the strongly stable ideal generated by that one, is you take that and all other monomials inside of there. So so there's that. Those are definitely not square free typically. And if you take the radical of this ideal, what do you get? Everyone has an x1 in it, so it's just going to be the ideal generated by x1. There's not much else going on there. I was thinking also of doing Hilbert functions. So what are people's comfort level with Hilbert functions? 0. Okay. Let me. We don't really need this for, but it's one of the best applications of Gröbner bases. So I think we will discuss it a little bit. And this seems like a good time to do it now because it's going to be we're going to do Gröbner, Hilbert functions of monomial ideals. So let's do that here. Hilbert functions and series, Hilbert series. For monomial ideals. I get really tired of writing monomial ideals, so for me it's mon ideals. Okay. So here's the basic idea is this can be done all in much more generality. We can take an arbitrary graded ring, for grading group, any abelian group and so on and so forth. But we're going to just do the very simple one now. So we're going to take R we call is k of x1 to xn, and we grade this by where we set the degrees that the degree of xi is all 1. Okay, this is the standard grading. Again, it really is not that relevant. I mean, you can change it, but this is by far the most useful one, at least when you start out. So there's this, and then you have the degree of e.g. x1, x2 squared is 3. It just adds like you would normally do degrees. And R we can write down as the direct sum over all D, well, in Z, because all these things are integers, but in fact it's D is greater or equal to 0 of R sub D, where R sub D is equal to the span of all degree D monomials. Okay. What is this equality? This always bothered me when I was first learning the game, that you write this down, and what is this? Is this an equality as rings, as sets, as abelian groups? What is it? Well, each one of these things has just the span. These are vector spaces here, or abelian groups if it were over Z, for instance. But it would be just that. And so this is as vector spaces. So it's isomorphic, they're equal as vector spaces. And these are the polynomials is homogeneous if it's in one of these guys. Homogeneous of degree D if it's inside of there. Okay, then the Hilbert might as well do part of it here. So then, given this, so if I is generated, let's do it in general here, F1 to FR. Okay, and each F sub I is homogeneous of some degree, not necessarily the same degree at all. So then we call, then I is called a homogeneous ideal. Okay, this I expect you all know this kind of stuff. Is that basically okay? So so we're going to start with a homogeneous ideal now, including any monomial ideal is homogeneous because each one has only one term, so it's nicely it's certainly homogeneous. And now, what's the Hilbert function? So the Hilbert function so H, let's call it Hilb. Hilb sub, I typically will do it for R mod I, but it doesn't really matter. R mod I, say, of D is the dimension over the base field K of R to the D, which is all polynomials, modulo the polynomials of degree D. Okay. Actually, this is true for any graded module. We could do the same thing, but this is the one that we care about for the moment most. So let's just leave it at this. That's this. So this is a bunch of numbers. One for here, D is any element in Z. Well, actually, it's 0 if it's not greater than or equal to 0. And so we have this. That's a bunch of infinite number of things. So the usual way, if you have an infinite number of things, you make a generating function out of it. And so the Hilbert series of R mod I is H sub R mod I of a parameter T. And this is going to be the formal power series for all T in Z. I guess not T, sorry, that's a bad name. Let's say D and Z. And it's going to be this, put all this guys in. Instead of writing Hilbert, I'll just write this down again. Of R mod I in degree D. That's the same thing as that. Times T to the D. Okay. I'm not sure who had the intuition that this was a really great thing to look at. But it certainly was Hilbert, if not, but probably earlier than that. And it's a really good intuition. The larger this is growing, it differentiates what the dimension of I is and things like that. So it's one of the good ways of getting lots of information. And Hilbert actually wanted to compute these things. But it's an infinite amount of information, apparently. But in fact, he proves in I think it's his 1890 paper, if I'm not mistaken, he proves that h of R mod I of t is a rational function. So it's going to be some polynomial f of t over 1 minus t to the number of variables, n. And f here is in z join t. So it's a polynomial with integer coefficients. But it's a polynomial. It's a finite amount of information. Okay, you gotta love it. Okay, how did Hilbert prove this? Okay. In one paper in 1890, he essentially creates all of commutative algebra. And this is the paper that he got a hard time for with the Hilbert basis theorem and things like that. And so what he does is he finds a way of computing syzygies, which was now erased, I think. He actually had an algorithm for doing it, which would be an interesting project to figure out. I was given that as an undergrad to implement, but it was all in German. I could hardly read it. But when I did it, I was obvious that this was like a horrendous way of doing it. And in fact, I couldn't. Certainly in the 1970s when I did this, it was, or early 1980s, there was no way that that would ever run. Now it might have a chance. We'd have to go back and take a look. Anyway, he proved that he gives an algorithm for computing syzygies. Then he shows that if you take the syzygies of the syzygies and so on and so forth, it's finite after a while. And then he uses that to show that this is a rational function. That is his proof. Nowadays, it's much slicker. You don't have to do any of that stuff. But it was still pretty impressive. This might have been the 1893 paper. I always forget. Okay.
Sir,
So, yep.
Sir, I have two questions. One thing is that in Hilb R by ID, in the first line, what is I subscript D?
Oh, I subscript D is the vector space of all spanned by all forms of degree D in I. Okay.
Okay.
So you could think of it as I intersect R sub D.
Okay.
Did you mean to write R mod I in degree D there? Because like otherwise RD mod ID is vector spaces, the quotient of vector spaces, did you mean?
Yeah, RD is a vector space, and ID is a subvector space of it. And so R sub D mod I sub D is precisely the same thing as the degree.
Okay, so you're
degree D
defining it
elements
as
in
that.
R mod
Okay.
I. Okay. So yeah, I did mean that. And I just did it this way up here. This is the way I would normally write it, but this is just to make sure that it's a nice friendly vector space computation. Actually, in this case, if D is negative, it's 0. There is nothing there. Okay. But the reason I do it this way is because if I have an arbitrary graded module, it might have stuff in negative degrees. And so we're going to be interested in that case. Here's the cool thing, though. Not only is H equal to this thing has a whole bunch of 1 minus t's in it, usually. So you can actually rewrite this as g of t over 1 minus t to some degree. Let's call that, I don't want to use d. Let's use, m, say, okay? So this is where g of 1 is not equal to 0, okay? So if g of t, if you factor through it by as many 1 minus t's as possible, then you'll get down to this form. And here you get that g is in z of t as well. I mean, you're just dividing by 1 minus t's whenever it factors. And also, the dimension, this is the Krull dimension, which we'll say more about other ways of doing it later. But this is the Krull dimension of R mod I is equal to m. It's actually very cool. So this power here is sort of the growth of this thing, and the growth is actually giving you the dimension, and it gives you huge amounts of other information. You get the genus of a curve, yeah, or you get the sectional genus of a surface, and you get all this other information from this thing. So the Hilbert function is really interesting, useful information about any sort of ideal or variety corresponding to the ideal. And now what I want to do is we want to figure out how to prove this. No, we're not going to prove this. That's for you to wonder for later. But in fact, actually, we probably will. Once we have free resolutions, it's a pretty easy process. I mean, it's really spectacular. Well, we haven't even defined a free resolution yet, but it's an exact sequence, complex of modules. There were not complexes at the time. So the way he writes it is very confusing, and at least it was for me at the time when I was looking at it. Okay, so here are some factoids about this. What's our timing, by the way? Okay, good. So so we can compute some of these things. So if I take HR of t, so this is a polynomial ring, I know how many monomials there are. I can just do a combinatorial argument to figure out how many there are. It's in degree d, it's d plus n minus 1 choose. So I don't even want to write it down, because what I really want to write down is that this thing has Hilbert function 1 minus t to the n, 1 over 1 minus t to the n. Okay, that's something, that's just a computation that you can do. Okay, and now let's do it. Actually, sorry, for some reason, that's the only factoid I have written down at the moment. We'll get to more later. So I forgot, I want to do an example here. Let's take a simple example. Let's take R of, let's do not R of. Exactly, yeah. So for instance, if you think about it, the dimension of R sub d over k is equal to d plus n minus 1, choose d or n minus 1. Okay. So this is, you have to do a combinatorial argument to pay attention. And then the way you see this is, how do you get that? Well, you take 1 plus t squared, which is 1 over 1 minus t. You differentiate a whole bunch of times, and that's what you basically get. Okay, so there's no reason, by the way, ahead of time that these things have to be rational functions like that. In fact, if you do this for certain other situations, they will not be, and that's a sort of big thing that we'll probably talk about at some point. But in this case, they are rational functions from Hilbert's theorem, and yeah, so we have that. So here, let's do a simple example. R is equal to k. Let's just do I'm not going to really do the example yet. X1, X2, X3, X4. And I is going to be equal to the ideal X1 squared, X1, X2, and X2 squared. I was just going to use A, B, C, D, but I decided to at least use this every now and then. So here's this. And now what is the Hilbert function of R mod I? Hilbert series, rather. Well, it turns out that we can compute this, and we'll see how to do that in just a bit. 1 plus 3t squared minus 2t cubed over 1 minus t to the 4th. However, you can also divide by the 1 minus t's. It turns out this has 2 factors of 1 minus t in it. And so when you get rid of that, you're left with 1 plus 2t over 1 minus t squared. Okay. So that's the Hilbert series. This 2 then means that the dimension of R mod I is 2. is that believable to you? So if you've are familiar with this, so the dimension of I will be the same as the dimension of the radical of I, which is the ideal given by x1 equals x2 equals 0. But that leaves two free variables, 3 and 4, so that's the dimension is 2.
There's some signs off there. That thing is not, doesn't have a zero.
This is yep. Thank you. Okay, so it's 1 minus 3t squared plus 2t cubed. Actually, it would have been, yeah, any number of, that's a good call. And so that we have that's the case. So now there is the question of how do you do this? So question, how to compute this? H of R mod I of t for I a monomial ideal. Okay. Here's an important exact sequence. This is true for any I homogeneous and I and F of say the degree of F is homogeneous of degree D. Okay, but we're going to mostly use it for monomial ideals right here and monomials. But so in that case, we have a map R mod I. So I'm given a F is not necessarily an I. In fact, it's not an I usually. Okay. So and I map it down to R mod I plus F. This is a surjective map. So we have a 0 here. What's the kernel of this map? So this is just this standard. It takes 1 to 1 and just mods out by more stuff. Okay. So what is the kernel? Just one of the isomorphism theorem things if, that you sometimes. So it's this mod I. Okay. This has maps of degree 0. So this is homogeneous. Every one of these things is homogeneous, and the maps are degree 0. Okay, what does it mean for a map to be homogeneous of degree 0? It means it takes homogeneous stuff here to the homogeneous stuff of the same degree. That's the 0. If it were homogeneous of degree 1, it would up the degree by 1. But we're not going to really ever use those so much. Most things we care about have degree 0. Okay, now, however, what is this thing? I plus F mod I. So note, I plus F mod I is isomorphic as graded modules, so you're not changing anything, to what? Here, let's actually write this down. Have I just done that up there? So we'll go over here. So let's see. So if I take R, I have a map from R to I plus F mod I. Okay. What is the map? It sends 1 to F. Okay. What's the kernel of this map? Okay, I get mod out by the kernel, and it's first of all, this maps onto this because all this stuff is 0, so it's mapping onto it. So this is 0, and then the kernel of it is going to be I colon F. Any polynomial here that multiplies by F that lands you at I is 0. So this is exactly this. However, this has degree D. Degree D. Okay, because it takes an element of degree 0 to an element of degree D. So what we do is we do this minus D here, and R of minus D is equal to R, except the gradient is changed, except R minus D in degree E is equal to R in degree minus D plus E. You have to blame Sarah on this one, okay? The fact is that this thing has its generator. So R is generated by one, right? One element has its generator in what degree? In degree D, right? Because we want degree D to go to degree D. One is going to F, and that's what this is. And that's what it is if you use this definition. Somehow it seems like it really should be R of D, but Serre, when he was doing his coherent sheaf cohomology stuff, used this definition instead, and we're stuck with it. Actually, it's an okay definition for, it's either, six of, you say tomato, I say tomato, I suppose, but it's something like this. But what we get here is that R mod I colon F shifted in degree D, okay, that's the same thing, is isomorphic to I plus F mod I. So we get the following exact sequence. And that the degree, not D anymore, the degree E part and the degree E part here are isomorphic to each other. So what we get is the following thing. We get 0 maps to R mod I colon F minus D, mapping to R mod I, mapping to R mod I plus F. And this is an exact sequence. And all the maps are degree 0, it's all graded, which that means, and so that tells us, so the degree, let's not use D here, the degree E part of each thing now. I shouldn't have used D for that. I colon F minus D, this whole thing in degree E, which is R E, well, except for the shift, you have to figure out what it is. It's on the stuff in R degree E minus D divided by the same submodule of the this thing that we did before. This goes to R mod I in degree E, and this goes to R mod I plus F in degree E, and that goes to 0. This is an exact sequence of vector spaces for all E and Z. Now, the great thing about vector spaces and this kind of thing is that the dimensions are additive, right? So the dimension of this one, therefore, is going to equal this one plus this one. And then when we multiply each of those dimensions by t to the whatever degree it is, t to the e, and then sum it all up, we get the corollary that the dimension of R mod I, we have two ways of thinking about it. This one is equal to, not the dimension. H of the middle guy, R mod I of t, is equal to the sum of these two. That's H of R mod I colon F of t, except there's this shift in degree. How does that get affected in the H? It's just a shift in degree, which means that it's going to be multiplied by t to the something or t to the minus something, there, and it turns out it's t to the d. That's this one, and then this one is just H of R mod I plus F of t. And this is a very cool, fairly straightforward once you do it, thing. It tells us a couple things. We have two ways of using this thing, and this is going to be part of what I want you to sort of play around with. But what you're going to get is, one way to do it is to do it iteratively, to use this. So I claim that this gives us an algorithm for computing. I mean, there's a few things to check, but it's not so bad. So one algorithm for H of R mod I of t where I is equal to x to the alpha 1, x to the alpha r, say, okay, would be what? It would be to use this iteratively. So we first figure out the for x. So suppose use the formula iteratively. But it's also a little bit of a recursive thing. So in other words, I shouldn't have used I here, rats, because that's not the I that's up there. Let's call this J here. Okay, we let I equal x to the alpha 1 up to x to the alpha r minus 1, and f will equal x to the alpha r. This would be one way to do it. This is the way when we first did this a long time ago, it was what we did. It's not the best way, but it is, sometimes it is. But anyway, we get this, and then we get that since J is equal to this plus this, what do we get? We get h of r mod I. That's this term here is equal to, so we get that that's equal to h of r mod I comma f. So just add in f. Sorry, J. Sorry, just J. This is the one. So this is J. So that's I plus f is equal to that. This is really screwed up, isn't it? No, actually, it's not. I plus f is equal to J. R mod I is. I see what I'm doing wrong. I want yeah, I want R. Sorry, I'm just getting confused about my notation since I did it on the board on the spot. So I want the Hilbert function of this. That is equal to the Hilbert function of this one. That's the that one is equal to that minus that. So that's this minus t to the d. Well, what is d here? That's the degree of x to the alpha r times h of r modulo the ideal I colon x to the alpha r of t. Okay, by induction, this has one less generator, so we can compute it. How about this one? Well, this one we know what the degree is. Does this have, how many generators does this have? Well, that's part of one of the things that you had to figure out before, but it has no more generators than I has, and the degrees are smaller. So that these can both be done. When I use the word iteratively, I'm being generous because it's really a tree structure. Now we have two different things to compute, and it looks like an exponential amount of work. And there are things you can do to improve that, but we're not going to worry about that right now. So this is the first algorithm where you can just really do it. And if you think of it in this term here, it's actually pretty straightforward. You can do it without that, but I think that this is a better way of thinking about it. Okay, it is now 11:10. I suggest we take a short break, 10 or 15 minutes, and then I have a sheet that you can play around with. You can try doing this on an example. You can try the other things. There's a couple other things that involve Gröbner bases, which maybe we'll save for a little later. Are there any questions before we take a break? Yeah, are there questions online?
Can I ask a quick question about the definition of Hilbert function? If you replace the field k with the integer z, what replaces the dimension?
That's a good question. It's not a Hilbert function anymore. So yeah, there's all sorts of things one could put there. You might want to use the length, for instance, of it as a module. It's probably what you want to use. That's a good question, though, because there are some of these things that in those kind of situations, we don't have ready-made algorithms to compute. So it would be already something very straightforward that we could try to make sure that we can compute. Even the length of a module is not always completely trivial.
So you would, sorry, is that you actually replace it with length, or is it like circumstantial, depending on what you're trying to compute?
Depends what you're trying to compute. What you won't get is anything like these results here, because
Okay.
that will not tell you the dimension in the setting.
Thank you.
I mean, there is the Hilbert-Samuel polynomial, which is maybe what you're thinking of, and that is something that we will discuss at some point.
Hello.
N-
Hi.
Other questions?
Yeah. So in the last equation that you've mentioned, I colon x bar alpha r, what if that is equal to I itself?
I'm sorry, what, this I colon x to the alpha x to the alpha
Yeah.
r?
Yeah, what if that is equal to I? You can't use the iterative equation.
You mean what if that is equal to I itself?
Can we use?
Yeah, then that would be great. Then you would only have to do this once, and you wouldn't have to do twice as much work.
Okay.
There are other things that you can get by with here, as if you take a look at the example that I've suggested, that sometimes it's easier. The base cases. I haven't told you where you should really start the base case here at. Should you go all the way down to 0, or can you do it with 1 generator or 2 generators? That can make a huge difference actually in runtime of these things as well. So,
Yeah.
But
Thanks.
by the way, before I do have one other thing that just to say. So this is something that Dave Beyer and I did a long time ago, is doing it this way. But since then, and so it was implemented sort of like this, it works out really quite well most of the time, but there are times when it's just awful. And Anna Bugatti had a different way of using this exact same formula, which was not to do it this way, but to say, I want to know I. I'm just going to choose a monomial outside of that, and then I get two things. That has a few, if you're used to combinatorial arguments, one really important thing is that it's now a sum of two things rather than a alternating sum, which is just a mess. So that actually turns out to be really good, and that's what we use in Macaulay 2 these days. So you have to choose F correctly though. So you have, oftentimes what you do is you could choose it to be a variable. There's a few other little heuristic tricks also. Anyway, so let's take a say 15-minute break, I think, and then we can come back here and work on some of those problems for a bit, and then at 1 o'clock, wait, no, not 1 o'clock. That's when it ends. At 12 o'clock, maybe we'll do more, and we'll do monomial orders and Gröbner bases and things like that. So do you all have the little sheet of problems that it's up from the website at Fields for the commutative algebra. Let's see, maybe I can also get mine on.
Where on the website?
That's an awesome question. Lynn put it on. So she showed me where, but I kind of forget.
I
send a link in the chat. So
Slides? Yes. Ah.
Oops, how do I have to find where the link is here? Okay, here it is. I see. So first of all, there's a questionnaire there. And then maybe if you, on lecture 1, you can click on it. And, oh yeah, it says slides. It's not really a slide, but it is the, oh, here, let me share my screen. I mean, sorry, not share it. I have to actually get on to Zoom. Where is the Zoom? Together on it. That's a good idea. Recording. Oops, I think is it probably Linda started. Okay, so are you okay with starting over? Starting over? Okay. So does anybody want to explain any of these? Or do you want to just do it together as a group? So I suggest we stay with these two because otherwise we won't have time for anything else. So where's my talk? Yes.
Just for future, when we're doing these problem sessions, when you write things on the board, do you recommend that we start with those ones and then do the others on our own, that kind of thing, or?
Probably.
Okay.
And the only reason I did that not having no clue what everyone's background was or anything where we were starting from or anything like that. And so that as we're going, I just thought these two would probably be good ones to start with. However, probably this is a good one to start with here because I sort of didn't have a proof in mind as when I was talking about it. I went, oh, it's maybe, you know, so let's just see if we can figure this out. So I think probably a good first thing is to figure out when a polynomial is in a monomial ideal, right? So let's suppose, so let's do B first. Oops. But first, let's consider, so if f is a polynomial, so c times, let's call this x to the beta 1, c1 plus c2 times x to the beta 2. We don't really need all this notation, I hope, but you never know. Cm x to the beta m is in R, okay, where these are field elements. And suppose that f and I here is alpha 1 x to the alpha 1, x to the alpha r. Then f is in I if and only if what holds. And maybe you didn't do it this way. And if that's okay, maybe you have a simpler way of doing it. Yeah, exactly. F is in I if and only if x to the beta I is in I for all I equals 1 to m. Okay? And how do you prove that? Well, suppose that f is in I, so it's going to be a multiple of something times it, whole polynomial times this, whole polynomial times that. Every single monomial in there is divisible by one of these things. So if there is some monomial in there that's not, it can't possibly be it. Okay, so that's sort of the way I was thinking of it. And then that gives us how we can get at this thing. So I colon x to the alpha should be what? Well, we're looking for the f times polynomials f times x to the alpha are in I, but because of this thing, really we can restrict to just looking at monomials. Okay. So this is equal to the monomials that when you multiply by x to the alpha, you land in there. So I think that is, so what is the answer come out to be since we didn't actually write it down earlier? So colon here is really taking x to the alpha 1. I have too many alphas, but x to the alpha. So this is just x to the alpha 1 sort of divided by x to the alpha, but of course, if it's not divisible, it's the smallest monomial that knocks it into that. X to the alpha 2 colon x to the alpha up to x to the alpha r colon x to the alpha. And x to the alpha, let's say x to the beta colon x to the alpha is actually pretty easy. This is x to the maximum. Let's say let me write it down this way. Product over I equals 1 to n of x sub I to the what is it? The maximum of 0 and beta I minus alpha I. That, right? So this is so basically that will be the smallest monomial that gets in here. So for instance, x1 squared colon x1 x3 is just x1. Anyway, so and the cool thing here is you have your generators and you just have to do all this. This might be not a minimal set of generators, though. You might be able to pare it down to a smaller set, which we saw happening in the example earlier. But it's no larger than R, so that when we're computing these things, things are going to be getting smaller typically, not just typically, provably. Is this enough detail on that one? How about problem 2? Or A? I screwed up. So I should have used the same lettering that was in the sheet. Sorry about that. So how about how would you do? Did anyone have a good way of doing this one? Yeah. I You mean not using the no, you got to use the algorithm. The reason is that so you're absolutely right. There's a much simpler way of doing this one without the algorithm. Basically, you just have to look at the monomials that don't involve. Is this what you were doing? Or did you have a? That's right. So that's interesting. Okay, so so one way to do it, which is actually an interesting way, is that R mod I is, you can write it as a tensor product if you want. So this is K of AB modulo A squared AB B squared. This is not the way I was suggesting you do it, but it's actually a good point to make anyway. So it's this thing, tensor over K of C and D, okay? This has a basis of all monomials of this times all monomials of this, and consequently the Hilbert function of R mod I here is equal to the product of the Hilbert functions here. So this is the Hilbert function of K of AB mod A squared AB B squared of T times the Hilbert function of this, but we already know that one because it's of 2 variables. So it's times 1 over 1 minus T squared. But this one's really easy. What is it? There's one thing in degree 0, 1. There's A and B in degree 2, that's 2, and then that's it. So this is equal to 1 plus 2t divided by 1 minus t squared. This is a good way to do it because, if, at least in this case, because then you don't have to if you now multiply it up to get 1 over 1 minus t to the 4th, that's multiplying this by 1 minus t squared, and you find that that is 1 minus 3t squared plus 2t cubed. Is how that works out. So that's one way to do it. This is, by the way, a very useful construction, even in this algorithm. Because if you ever find yourself in a situation when your ideal doesn't depend on some variables, you can do this and really simplify your life quite a lot. But, okay, that's one way. So now let's do it by the algorithm. So the question is, let's do it iteratively. So so what I'm going to do is I'm going to take H of R mod, R mod A squared, okay, of T. What is this equal to? This one you can essentially do by, actually, how do you do it? This is the base case. Okay, so a single monomial will, it's 1 minus t squared over 1 minus t to the 4th is what it is. Because the other 3 variables are going to give you the 1 minus t's that you had before, and then here you have 1 plus t, and then to get it up to, you have to multiply by 1 minus t to get it up to that. So it's 1 plus t times 1 minus t gives you this. So this is, so there's some base case here that you have to do. So in fact, I think, let's see, what is H of R mod any specific monomial x to the alpha? Later, we'll see exactly. This can be done using free resolutions really trivially. And this is 1 minus the degree of alpha, degree of x to the alpha. Oops, t to that. T to the degree of x to the alpha divided by 1 minus t to the number of variables. So this is a base case in general. So that's kind of nice to start with. Okay, now what we do is we do it up iteratively. So so then we have R mod A squared mapping down to R mod a squared comma ab. Okay, like this. And then the kernel was the R modulo the ideal quotient. So what's the quotient? What knocks a squared into the previous stuff? AB. Sorry, what knocks AB into a squared? Just A, right? So that's going to be R mod A. But it's twisted now by the degree of this thing, which is 2. So now we can get this one by the equation. So we get Hilb of R mod A squared AB is equal to this one, Hilb of R mod A squared minus this, that minus 2 becomes a T squared, and then it's Hilb of, sorry, of what? Of the colon, right? That which is A, R mod A. Okay, of T. And now this one is pretty good. What is it? H of R mod A squared? That's what we had before. That's 1 minus T squared over 1 minus T to the 4th. The first thing you notice is that every single one of these will have a 1 over 1 minus T to the 4th in them. So really, we could just sort of ignore that too, if you wanted. But here we get T squared, and R mod A is, we didn't write that one down. H of R mod A is 1 minus T over 1 minus T to the 4th by this same thing, which is 1 over 1 minus T cubed if you want. But we don't want, we want this version of it since we have, that's what all of our denominators are going to be. So we get 1 over T squared times 1 minus T over 1 minus T to the 4th. So when I just add that out, I get 1 minus T squared minus another T squared minus 2T squared, and then plus a T cubed here over 1 minus T to the 4th. Okay. This is also completely clear once we do the free resolution of it, and we can compute it that way. And then now we do the third one. So R mod, so now we do R mod A squared AB mapping down to R mod A squared AB B squared. I mean, this is an awful way to do it. Got to tell you, for this particular example, that way over there is much preferable, but this one generalizes it. You get to see the structure of how it works in general. So, so that's why we're doing this one, and it's not so large that you get completely lost in all the symbols. I hope. So anyway, so here, what goes over here now? This is R modulo. What knocks B squared into AB and B squared? So what is A squared AB colon B squared? This one would be A squared, and that one would be A. So it's just A. Okay. So this is R mod A again with a shift of -2. And so then we get that the Hilbert series of R mod I, the one that we really care about, is equal to this Hilbert series, which is 1 minus 2T squared minus plus T cubed over 1 minus T to the 4th. Minus that one, minus, and there's a T squared again, and again, another 1 minus T over 1 minus T to the 4th. And in practice, you would not carry along all these 1 minus T to the 4th. And that is 1 minus 2 minus another T squared, that's minus 3T squared, plus a T cubed and another one, plus 2T cubed over 1 minus T to the 4th. And then if you really wanted to multiply that down, that is going to be, it factors out 2, and you get 1 plus 2T, which is what you get immediately the other way. So actually, you can get either one the other way, but this is what you have. Was that okay, or should I? Maybe I should let you guys come to the board and do these things also. In the future, maybe we'll try to do that because it's probably a little more instructive. Maybe you'll have better ways of doing it than I do, also. So, okay.
Excuse me.
Question?
It's 1 plus 2t by 1 minus e to the power 4 or 2?
I'm sorry, I can't hear you.
It's 1 plus 2t by 1 minus e to the power 4 or 2. The denominator
That's
is
2. This is 1 plus 2t over 1 minus t
Okay,
quantity
okay.
squared, because there are two
Okay.
factors of 1 minus t here.
Okay. Thank you.
At least I think that should be the case. Okay, so now we're going to go on and do monomial orders and Gröbner bases and get that down. Okay, so I wasn't going to really give the whole usual shtick that I do for when I first introduce the Gröbner basis. The question is, why do we do it? We have a bunch of generators for the ideal. In certain cases, we can understand everything about the ideal. What are those cases? Case 1 is if we're in one variable. You take a whole bunch of generators, and what is the ideal generated by, actually? The GCD of every single one of those, right? It's in one variable, it's a PID, the whole thing. So we have one generator, and that would be the Gröbner basis here, okay? But how you find that might be you have to do a lot of work to figure out that GCD. Another case that works nicely is if you're doing Gaussian reduction for linear polynomials. Suppose my ideal is generated by linear polynomials, not necessarily homogeneous, just linear in a constant term. I can do Gaussian elimination on that, think of it as a matrix, and then I get a nicer set of generators where lots of things are just immediately understood. Okay? The whole point of Gröbner basis is to generalize those two things. One variable, high degree, n variables, degree 1. But in the middle case, what do? You're in 5 variables and you have things of degree 3, or 10, I mean, some ridiculous thing, and you have these huge polynomials. How do you do the same kind of thing? Well, the idea is that in those two cases, in K of x, we had a natural monomial order. We had 1 is less than x squared, and so on. Okay, and then we could just think of it that way. And in K of x1 to xn, are linear, then we just had to choose an order on the variables. So maybe x1 is greater than x2, is like this. And so that when you look at it, you look at the lead term. These are like the pivots that you would get, or the reducers in Gaussian elimination. So I don't really want to spend huge amounts of time on that thing, but that's the is that a relatively okay description, or is that totally not good to give it that amount? The trouble, the point is that now if we have to go to higher than linear, we have to figure out a way of ordering the monomials. And that's going to be important how we do it. And it's actually pretty cool because different ways of ordering it are going to give us different behaviors of what the result is. And we're going to make use of that. So here is the first definition. So well, first of all, the idea is we want to order the monomials. Monomials, let's spell it right. Want to order the monomials of R such that if f is equal to a polynomial, c1 x to the alpha 1 plus ... plus cm to the x to the alpha m, just like we had before, and suppose that we have already got it so that these are in descending order. Okay, so we've got the polynomials sorted with whatever order we're using. Then what we really want is that if I multiply it by something, I don't completely mess up the order, right? Then I want that x to the gamma, or beta, say, times f stays in order. In other words, that x to the alpha 1 plus beta is greater than x to the alpha 2 plus beta all the way down. That is really what we want, that the whole property of it, or that's one of the two properties we want. The other property we want is we don't want 1 to be the lead term ever, because we're going to get into infinite loops in that kind of case. So So let's see what that, let's actually say what this means for the order. So definition. A global monomial order greater than on R. Okay, the global is just going to have this, we'll say something about it. Monomial order, sometimes you also use the word multiplicative order. I've seen it in both I've personally used it in both ways all the time. But anyway, so this is a total order on the monomials of R, satisfying two properties. A, that x to the alpha is greater than 1 for all x to the alpha not equal to 1. Okay, so it's the very, 1 is the very smallest element that there is. So remember, 1 is just when the alpha is all zeros. And the second one is precisely this thing up here, but you don't need to have a whole polynomial, you just have to have 2. If x to the alpha is greater than x to the beta, and x to the gamma is any monomial, then x to the alpha times x to the gamma, or x to the alpha plus gamma, is greater than x to the beta times x to the gamma. Okay, so this ensures that it always stays sorted. So otherwise, all the algorithms will really mess up badly, and this ensures finiteness somehow or another, as it will turn out. Okay, what are some examples of this? Guess I'll get rid of this now. Only the first example is the lexicographic order. So examples. Oops, I was going to do something else first, but I'll do the examples first. Okay, first one is lexicographic order, lex order. And this is x to the alpha is greater than x to the beta. So this is, here we have a choice of how we order the variables. So we're going to try to order all these orders so that the variables are in order. We could permute them and everything. That would be another possibility. But I'm going to assume that I have this. And then this is this if and only if two things, if and only if, well, I want that the highest power, you look at the first variable first. I mean, it's the word order basically, and I want it to appear first. So if I write it out as a word, so really one way to think about this is that if I take alpha minus beta, the vector alpha minus beta, oops, the first entry, first non-zero entry of the vector alpha minus beta is positive. So e.g., x1 is greater than x2 to the 1000. Okay, because this is a 1, 0 and this is a 0, 1000. Okay, which is greater than x2 to the times x3 to the 5. I don't know. And then greater than 1. Okay, so we have all of these kinds of things. So that's the lexicographic order. It's clear that if I multiply by adding by gamma, that it's the case. It's also clear that A holds for that. That's the smallest one. The next one is graded lexicographic order. Again, we're always taking x1 is greater than xn here. Then otherwise we just permute them first and then do this process. And it's a useful thing. I mean, it's possible that changing the order just by permuting them, even whatever order I take, or Gröbner basis, is going to give a huge different result. So and so we have to. It really should be considered as separate. But anyway, so suppose we have this. x to the alpha is greater than x to the beta if and only if the degree of x to the alpha is greater than degree of x to the beta. That's the graded part. Or we have equality. And what happens above and let's say this is lex here. And x to the alpha is greater than lex x to the beta. So I should actually say this. Let's call this G lex for graded lex. Okay. That's in order. And then here is one. This is called the graded reverse lexicographic order. We'll do examples of. Now, normally all I would have to do, graded would be do this and then take the opposite of this. But that gives me an order where xn is greater than this. So I want to switch it around so that x1 is still greater than up to xn like this. And what this is that x to the alpha is greater than x to the beta in Gröbner order. If and only if the degree of x to the alpha is greater than the degree of x to the beta. Or we have equality and we want to invert this. I want to say that is negative, but since I'm inverting the variables, it's going to be the last non-zero, the last non-zero entry of alpha minus beta. And there it was positive, and here it's negative. It's a little weird, okay? But we're going to do an example in just a second, so you'll see it. You might say, well, wait a second, why not just the reverse lexicographic order without the graded? Do you see any problems with that? Have to, I mean, until you actually internalize these things, it's not so easy to just sort of see it, but it's going to be a problem because if I take 1 in x to the, just say 1 in x, if I don't have that, the last non-zero entry of this is negative, puts 1 larger than anything else. So that would fail. So graded reverse lex order is what we will use. These are the 3 main orders, but there's others. They're so-called block orders or product orders and elimination orders. And so we'll discuss those, but not right at the moment. However, I do want to sort of show what happened, how these things differ a little bit. So I want to do an example. So before I write down the example, we haven't said what a Gröbner basis is, but it's going to be a bunch of polynomials, and it's going to have these lead terms. And we're going to think of those as pivots somehow. And then we're going to try to uncover new pivots, like in the Gaussian elimination routine, where you find which ones are non-zero. So we want to do that. So what we're doing is we're going further down in the order. And so we're going to take pivots that are at the beginning of the order. Okay, so here's an example. Let's consider x1 greater than x2 greater than x3. What are the possible orders on this? Let's only consider degree 2 polynomials. 2 monomials. Okay. In this case, the graded won't be relevant because everything's going to have the same degree that we consider. And so lex and graded lex would be the same. But from the multiplicative property of these things, and this is equal to a global, if I don't use the word, if I leave out the word global, it just means global. This is a monomial order, Mon order, that satisfies this. Then if I multiply this by any variable, I'm going to get whole lots of things. So it's going to say that x1 squared is greater than x1 x2. Which is greater than x1, x3 over here. Except I don't want that one there yet. Okay. Also, if I multiply by x2, so I'm going to get that this is greater than x1, x3, say. And I'm also going to have x2 squared here. This is greater than x2 squared. It doesn't tell me which one of these two I have, but then both of these are going to be greater than x2, x3, and that's going to be greater than x3 squared. So on these 6 monomials, 3, 4, 5, 6, there's only 2 possible monomial orders that differentiate these two things. Whether this one is before that or this one is before that. It has to be a total monomial, a total order. So so which one is which? So let's let Lex order is going to be x1 squared is greater than x1, x2 is greater than x1, x3 because it has the x1s out front. Given, and then that leaves x2 squared. Both of these are greater than this, x2, x3, and x3 squared. Whereas Grevlex is going to be x1 squared greater than x1, x2. And now these two change places. X2 squared is greater than x1, x3. Because now we're looking at the least power of x3, which this has smaller power of x3. These all have least powers of x3. So it's that's the way it goes. And then x2, x3, and x3 squared. So it's these two here that change. Looks pretty, innocuous. 2 little itty bitty things change. So do you notice anything about either of these 2 sets though? It's really kind of interesting. Here, the way the algorithm will work is it will try to uncover monomials starting from the beginning and then going deeper. If you ever get to a monomial that this is the lead term, notice that that polynomial doesn't involve x1 at all. So you've eliminated the variable x1 somehow. Whereas what about here? It'll get these. If you get down to this one, then it's something here. It's not in any subring like x2, x3, but it's all divisible by x3. Those are hugely different properties. So these two things, it really explains the difference between Lex and Grevlex in a nutshell. Except not really, because one of the examples on the third problem I put on, you can try it at home. Will show you a fairly dramatic difference between the two as well. Okay, so at any rate, so these are the at the moment the monomial orders we're going to use. There's a couple properties of them that we really want to make sure we have. And proposition, a monomial order, monorder, is a well ordering. I.e., any finite set of monomials, no, any set of monomials, not finite set, any set of monomials has a least element. This is not true if the order is the opposite. 1 is greater than x greater than x squared, because if I take all those monomials, there's no least element in there. But this is a really easy proposition. So proof, do it yourself. Use that R is Noetherian. Okay, you might say, well, that's cheating. But it's not really cheating because we proved that some other way. Okay, so anyway. By the way, Hilbert proved that R was Noetherian using this way that really irked at people at the time. And Gordon, I think it was in 1889. At least I haven't actually checked this, but in 1889, Gordon, well, I guess he gave an explicit proof of that R was Noetherian. And his explicit proof was essentially Gröbner bases. So Gröbner bases have in some form or another been around for quite a while. Okay, so anyway, that's a proposition that's sort of good. Here's another. No, we don't need that. Okay, so now I want to do some notation. So remember, we're in the ring R, the polynomial ring R. And let's let this be a monomial order, monorder on R. Okay, and let's let F be a polynomial in R. Maybe F is not equal to 0, because otherwise we have to deal with it. But so Lm of f, or actually, let's write it out. F is equal to C1 times x to the alpha 1 plus dot 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 plus C m times x to the alpha m, where x to the alpha 1 is greater than dot 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 is greater than x to the alpha m. So there's a number of things we could actually want from this to have special notation for. So that one of them is the lead. So if we need to, we'll say what the order is, but if not, we'll just leave it out. And this lead monomial is going to be x to the alpha 1, the very highest one that appears. Later, when we do other polynomial rings, this is especially useful. Lead term of f, again with the adorn, this is going to be the whole lead term, SC1 times x to the alpha 1. That just is kind of nice sometimes. And then the lead coefficient, I don't know what notation we'll use because this is kind of annoying. LC of f is just C1. And f is monic if C1 is, so f is monic means that C1 is equal to 1. Okay, just like in one variable case. So this is just some notation about this. And what we can do now is I think what we should do is just first define, I have a slightly different order here, but let's define a Gröbner basis first, just to have it done. So definition, let's let I contained in R be an ideal. And let's let greater than be a monoorder. Okay? And what we want is, I want to know what all the possible lead terms or lead monomials can be. So define Lm of I is equal to the lead term ideal or lead monomial ideal. The terms that really don't matter because since it's over a field, you can multiply or divide by them at will. This is going to equal the ideal generated by the lead monomial of every f, where f is in I guess not equal to 0. Okay. So this is a monomial ideal, which is the whole reason we did monomial ideals. It's the second reason we did, by the way, I saw there was a question on the chat. Why are we doing Hilbert series? You know, what difference does it make? Well, it's going to turn out that the Hilbert series of this and the Hilbert series of I are the same thing. And so this is a way of computing it in general. And that's one of the actual best applications of well, that's a judgment call, but it's a good one in any case. So the monomial ideal associated to I, and it depends on the monomial order. Okay, that's definition. And now another definition is, let's let G equal a set of elements F1 to Fr. And so here it's a subset. Typically, for what we're going to do is it can be a set, but I oftentimes will also want it to be an ordered set. Okay, a list of things. And this is be a list of non-zero elements. Of R. So G, and we're also fix a monomial order greater than. Then G is a Gröbner basis. Which I will almost always write as GB, like that, is a Gröbner basis for I, for an ideal I, if two things hold. The first one, surprise, surprise, is that each f sub I had better be in I. Okay, in fact, that's the main thing about that. And then the second one is that G really covers all the possible monomials you can get out of here. Okay, So how do I say that then? Then if I look at the lead monomials of I, that's an ideal, that is equal to the ideal generated by the lead monomial of F1 all the way up to the lead monomial of F to the R, F sub R. Okay. So these are certainly, FIs are in there, so certainly each of these lead monomials is in here. The hard part is that it's a Gröbner basis when that's it and everything is there. So as long as this does that, that is a Gröbner basis. And Gröbner bases are going to exist for all ideals. Okay, so that's not a problem. Notice two things though. In my definition, it's a finite list, not an infinite thing. For instance, if it were infinite, I could choose my set to be all of I, except for the zero element maybe, and then that would certainly be the case here, except for But here's another definition. This is a Gröbner basis G, which is the set F1 to FR, say, of I, is called, there are three things here. A is called minimal if these minimally generate this. If the lead monomials of F1 to lead monomials of FR are minimal generators, which means they don't divide each other, are incomparable in the divisibility order. That's a stupid way of saying it. But no one divides the other. Okay, and in particular, no two are equal. That's minimal. B, it's monic if the lead term of each Fi is equal, say the lead coefficient of each Fi. Lead coefficient of each Fi is equal to 1 for all I. Okay, makes sense that would be that. And the third one is G is reduced. If no term in Fi is divisible by any of the other lead terms, by any of lead monomials of Fj for j not equal to I. So in other words, I don't have any it's minimal if these things are incomparable, but if this particular one divides some polynomial in here, some monomial that appears in here, we want that to not be the case. Turns out it seems like more work to make sure it's reduced, but actually in computation it's much better usually, and it also gives you uniqueness. So in fact, let's go over to the other side. Okay, so in fact, if you think about it, once you have a Gröbner basis, it's really easy to get these things. Monic, really easy. You just divide them by the coefficient. These, you just take a set of generators and throw the others out. And then reduced, you have to maybe do a little bit of work, and that's what that's going to be part of the division algorithm, which we're going to talk about now. Where is my division algorithm? I'm doing things all out of order on my notes. Okay, so again, fix a monomial order. Right there. And let's let F1 to FR be an ordered list. Of non-zero polynomials. Okay, and let's let G be an element of R. I want to do division. if I do just division of a polynomial with respect to one polynomial over a field, you all know how to do that. But how do I do it with respect to all of them? So how do I do it with respect to one? I take this thing and I subtract off some multiple of this that will cancel the lead term. And then I get some other thing, and now it's rinse and repeat. I just keep doing it. Okay, so here is the division algorithm. I'm going to write it as an algorithm. I don't know if this is a good way to do it. Let's do it up here. So the algorithm is going to give us, we're going to get a divisor, which is 0, and a remainder, which is they both start off at 0. Okay, and while G is not equal to 0, do the following stuff. So if I is minimal such that the lead monomial of Fi divides the lead monomial of G. Okay. It might not be one, in which case we have to deal with it. Then, in parentheses, I'm going to say, suppose the lead term of G is equal to C times x to the beta times the lead term of Fi. Okay, so if it divides it, then there will be some constant maybe, but otherwise it's something like that. Then, and what I want to do is the divisor is going to be take this thing and add C times x to the beta times Fi. Okay. So if this is going to cancel the lead term of G and this thing here. So I'll get something of lower thing, and the remainder. Oops, no, the remainder stays the same. But G itself we have to change. So G is going to be G minus C times x to the beta Fi. Okay, so this is just the usual division algorithm on that one thing. Okay, for this one monomial, and I'm choosing it minimal. That's the ordered part here, just to make it deterministic, but also for other reasons that we'll see. Now else, okay, else means that there is none of them divide at all. In this case, what we want is we're going to set the remainder. We're going to add that term to the remainder, plus the LM is the lead monomial. Lead term includes the coefficient. So this is just a sneaky way of saying that in order to cancel this term, this is what I have to multiply by. Okay, but yeah, so LM, there's a difference between monomial and term here, definitely, that's being used. And here I'm doing lead term because I want whatever coefficient there is there, I want it to go along. And then G is just going to be G minus that lead term of G. Okay, this is the algorithm. And then it goes until G is 0. And it has to go because at every single time along the way, either G is 0 or this is a lower term, and the well ordering of the property of the thing means that this is finite. Okay, so then we return div and rem. Okay. And so what do we get for that? We have 5 minutes left. How are you all doing? This is 3 hours is pretty intense, no matter how you look at it. So, oh, I'm pretty pumped. Being up in front gives me a one up on you guys in that regard. Okay, so then what we get here is that therefore what we have is that G, I probably should have if I look at it each time, I'm for my divisor thing, I'm always adding something times one of the Fi's. So what I'm going to get here is that G is going to be the sum of some GI times Fi, where GI is the sum of all the ones that correspond to that, plus the remainder, which I called that. So let's just call that R here. Okay. Therefore, G is equal to this. This is I equals 1 to R, I guess is how many we had. And this is a uniquely presented thing, is completely uniquely determined. By the way, if you change the order of the Fs, it could be totally different, okay? But as given, this is it. And this terminates, okay? So this terminates. And I just said y, but I'm just gonna put y here and make it and have you at least verify that that you got that. Let's see. So here's some notation that we're going to use. So I'm going to say G here is equal to G//F plus G%F. And another name for this would be the remainder of F with respect to G. So this is the, oops, this is not right. This is times F here. Wait, is that the order I want it to be in? So this F is a, sorry, let me write this better. This is going to be G//F times the vector F1 to FR plus the remainder of this, which is either of these two things, say rem of F semicolon G. Okay, what is this? This is an R by 1 matrix. This is a 1 by R matrix of all of these GIs. Okay, so this is equal to G1 to GR. So this is the thing. These are the notations you might use in Macaulay tube. And these are unique. I mean, there were no choices made in this algorithm as is. Let's see. So let's not do the simple example. Let me just state the theorem. So let's let this be a bound order on R. And let's let F1 to FR be ordered, be in R, non-zero and ordered. And then for every G in R, there exists uniquely determined G1 up to GR in R. This is exactly the way I teach this in my undergraduate algebra class. When I do division algorithm in one variable, you do the algorithm first. Maybe I would do an example. I should have done one here, but I'm running out of time. And then I state it as a you get this thing out with certain properties, right? And so what are those properties? There exists this and a remainder. I'm going to use H, I guess, just to keep it from part of the algorithm, such that three things hold. One is that G is equal to G1 F1 plus ... plus GR FR plus H. That's the key property that we have. But we have more in it because we know something about what happens with the monomials in each one of these things. Two, no term, this is the hard one actually, no term of G sub I times the lead monomial of Fi. Those are exactly what are being used up in that section. We're taking that times the lead term or the lead monomial of that. No term of this is divisible by any lead monomial of Fj for j less than I. That's this minimal thing that's going on there. So because I'm choosing the smallest one that divides it, none of these smaller ones could possibly divide that term, okay? And the third thing is that no term of H, no term of H, the remainder, is in the ideal LM of F1, LM of FR. If it were, we would actually remove it. What? No term of capital G. Oh, here, good point. Yeah. That's, okay, it's even bad naming because it's not, it's really this, okay? It's the set of polynomials I'm dividing by.
That'd be the remainder. G by big G.
Okay, I'm really screwing it up. This is not. How about we say the following? Remainder of G by the set F1 to FR. And it's actually the list of F1 to FR. It's ordered. You know. So in fact, make it ordered by doing something like that. Yeah, right. That thing there. Okay. So, but this is pretty good. This is what you, of course, what you want. This is saying that if you take a polynomial in the ideal and you do this, you're going to get another polynomial in the ideal because this is all in the ideal, and it will have a new lead term, or it'll be 0. Okay, and that's going to be all we need to well, that and one more step to get a computation for Gröbner bases. But what we're going to do next time is we're going to also talk about the computation of syzygies, because it turns out that the easiest way to prove that we finally get a Gröbner base, how we compute the Gröbner basis, is using that, and it gives us a lot of the benefits of some of the so-called criteria that where you don't have to use all the S pairs and things like this. But we'll talk about that all next time. And we'll also talk about applications, other applications, like, yeah, that's probably what we'll be doing next time for this. And hopefully maybe move on to some homological things. I'll give you the every person's guide to extentor, for instance, or things like that. I have to think about how much time that's all going to take. But anyway, great. So see you next week.